A celestial object is defying the laws of physics as it is apparently rushing towards our planet. NASA and European agencies are on a bit of a high alert, and the United Nations International Asteroid Warning Network is also very closely watching.
Atlas did not return quietly, and its sudden behavior caught the attention of scientists far beyond astronomy circles. Within days, researchers noticed its path drifting off course, its speed rising beyond what gravity alone should allow, and its long comet tail fading almost out of sight. Then came the moment that raised even more eyebrows, a confirmed radio signal linked to the object itself. This was no longer just a strange visitor passing through space, but a case serious enough for NASA to watch closely and lawmakers to ask questions. So what exactly are we seeing here? A rare natural comet, or something that challenges how we understand interstellar objects? To answer that, we must first look at what happened when 3I Atlas disappeared, then came back. The moment Atlas passed, Perihelion marked a turning point that changed how scientists looked at this interstellar visitor. Perihelion is the point in an object's orbit where it comes closest to the Sun, and for most comets, this moment follows a familiar pattern. As they approach the Sun, heat increases, ice begins to sublimate, and activity grows stronger. Then, after perihelion, many comets either fade or break apart, leaving behind dust, gas, and predictable debris. This cycle is well understood, which is why what happened next with Atlas felt unsettling to many researchers. As it moved behind the Sun from Earth's point of view, Atlas temporarily disappeared from telescopes. This was not unusual by itself, since the glare of the Sun often hides objects during this stage. What mattered was what scientists expected to see when it returned. Based on earlier observations, many assumed they would find signs of stress, surface damage, or at least a clear change in behavior caused by extreme solar heating. Instead, when the object reappeared, the data told a very different story. Rather than showing chaos or weakness, Atlas came back active, structured, and strangely stable. Its brightness profile did not match what astronomers normally see after such a close solar encounter. The motion also raised eyebrows because its path did not fully align with earlier gravity-based predictions. This was the moment when individual oddities began to overlap. A single anomaly can often be dismissed, but several appearing together demand attention. Scientists realized they were no longer dealing with a routine post-perihelion comet. Another detail that stood out was timing. The return happened during a window when solar radiation should have caused visible changes on the surface. Yet the object did not behave like one that had just survived extreme heating. Instead of losing activity quickly, it maintained a steady presence that suggested internal processes were still at work. This persistence hinted that the materials inside Atlas might react to heat differently from those found in comets born within our own solar system. This unexpected stability forced researchers to slow down and recheck their assumptions. If Atlas formed around another star, then its structure, chemistry, and thermal response could follow rules shaped by a completely different environment. What looks strange through the lens of our solar system might be normal elsewhere. At the same time, this idea did not remove the mystery. It deepened it. Understanding the return of Atlas meant accepting that familiar models might not apply cleanly to interstellar objects. By the time scientists finished analyzing its reappearance, one thing became clear. The return from perihelion was not just another step in its journey, but the point where questions began to stack instead of fade. Each new dataset added weight to the sense that this object deserved closer and more careful study. And with that realization came a new question that could not be ignored. If the Sun did not break Atlas or slow it down, then what exactly is it made of? The chemical makeup of Atlas is the detail that quietly pushed scientists from curiosity into real concern. When astronomers study a comet, they expect certain patterns, especially in how ice and gas behave as sunlight heats the surface. Most comets from our solar system release water vapor as their main component, with carbon dioxide playing a secondary role. In the case of Atlas, that balance looked very different, and the numbers alone were enough to slow down the conversation in research rooms. Observations showed that the ratio of carbon dioxide to water was far higher than what scientists normally measure in native comets. This was not a small difference that could be brushed aside as measurement noise. It pointed to a body that either formed in much colder conditions or followed a chemical history unlike anything shaped by our Sun. For researchers who spend their careers comparing comet samples, this shift was a clear signal that Atlas did not share the same birthplace as the icy visitors we know so well. The surprise did not stop there. As the object released gas, instruments picked up clear signs of nickel compounds. On its own, nickel is not unheard of in space, but it rarely appears without iron when comets heat up and shed material. In Atlas, iron was strangely absent. This imbalance challenged standard models of how solid material forms and survives inside small bodies. Scientists had to consider that the internal structure of this object might be layered or bound in a way that prevents iron from escaping. Even under intense solar heating. To make sense of this, astronomers compared Atlas directly with well-studied comets from our solar system. Those familiar objects tend to show predictable chemical fingerprints because they formed from the same rotating disk of dust and gas around the young sun. Their compositions reflect a shared environment and a shared history. By contrast, the chemical signals from Atlas felt foreign. They suggested an origin shaped by a different star, different radiation levels, and possibly a different timeline of cooling and compression. This difference matters because chemistry acts like a record of birthplace. Just as soil can tell us where a plant grew, the gases released by a comet reveal the conditions it once lived in. The carbon-rich output and the unusual metal signature of Atlas imply a formation zone that does not match our solar system's recipe. That does not mean the object is artificial, but it does mean it carries information from a place we have never directly studied before. For scientists, this realization was both exciting and unsettling. It confirmed that interstellar visitors are not just rare versions of familiar objects, but true outsiders with their own rules. At the same time, chemistry alone could not explain every strange behavior already observed. The makeup of Atlas raised new questions rather than closing old ones. And that led researchers to look beyond what it is made of and start asking how those materials might influence the way it moves through space. If its chemistry is so unusual, could it also explain the strange changes in its motion? The movement of Atlas became truly unsettling when scientists realized gravity alone could not explain what they were seeing. In space, motion usually follows clear rules, especially for small objects like comets, whose paths can be predicted with high accuracy once their mass and position are known. For Atlas, those predictions began to fail. Its trajectory slowly drifted away from calculated models, not by chance, but in a measurable and repeatable way. Researchers identified what is known as non-gravitational acceleration, which means the object was gaining speed from forces other than gravity. This does not mean something artificial was pushing it, but it does mean an extra source of motion had to be present. What made this case stand out was the structure of that acceleration. It was not a single push in one direction. Instead, it appeared as two distinct components acting at the same time. The first component pushed Atlas directly away from the Sun. Measurements showed this outward force added roughly 83.9 miles per day squared to its motion. The number may sound abstract, but the idea is simple. Each day, the object moved just a little faster than the day before. That increase was small, yet it kept adding up. Over days and weeks, the gap between where the comet should have been and where it actually was became impossible to ignore. The second component was even more intriguing because it acted sideways rather than straight out. This transverse force measured about 37.3 miles per day, squared and gently nudged the object off its expected line. While weaker than the outward push, it played a key role in reshaping the overall path. Together, these two forces explained why Atlas did not simply speed up, but also drifted away from its predicted course. To understand what could cause this behavior, scientists turned to a familiar process seen in many comets. As ice heats up, trapped gases escape from the surface, creating tiny jets. Each jet produces a small reaction force, similar to how air leaving a balloon causes it to move. In the case of Atlas, this outgassing acted like countless microscopic thrusters. On their own, they were weak, but combined, they were strong enough to alter the object's motion in a detectable way. Studies estimated the total force involved was only a few millionths of a meter per second squared, which is incredibly small by everyday standards, yet powerful in the empty quiet of space. What made this acceleration especially important was not its strength, but its precision. The forces behaved consistently instead of randomly, suggesting the object's structure allowed gas to escape in stable directions. This stability hinted at an internal makeup that responds to heat in an organized way, rather than cracking or breaking apart. For an interstellar visitor, that alone was remarkable. Still, even with a natural explanation on the table, the acceleration did something else. It reopened old debates and reminded scientists of earlier surprises from objects beyond our solar system. The motion of Atlas did not prove anything extraordinary, but it showed that interstellar bodies can behave in ways that push our models to their limits. And that leads to the next question. If this kind of acceleration has appeared before, have we seen it in another visitor that sparked even bigger controversy? The strange behavior of Atlas immediately brought back memories of another visitor that once shook the scientific world. In 2017, astronomers discovered Oumuamua, the first known object confirmed to have entered our solar system from interstellar space. At first, it looked like a routine discovery. Yet as data improved, its motion began to defy expectations. Like Atlas, Oumuamua showed signs of acceleration that could not be explained by gravity alone, and that similarity is what caused scientists to pause. When Oumuamua moved away from the Sun, it gained speed without showing the clear gas clouds normally seen around comets. This puzzled researchers because there was no obvious source for the extra push. The mystery deepened when detailed models showed that the acceleration followed a smooth pattern rather than a random one. For many experts, this raised a difficult question. If gas was responsible, why could it not be clearly detected? And if it was not gas, what else could be causing the motion? This is where Avi Loeb entered the conversation. As a professor at Harvard, Loeb became widely known for suggesting that Oumuamua's behavior could be consistent with a thin object pushed by sunlight, similar to a solar sail. His idea did not claim proof of alien technology, but it challenged scientists to consider explanations beyond the usual categories. Loeb argued that science advances by testing uncomfortable possibilities, not by avoiding them. This approach made him a central figure in public discussions, even as many researchers disagreed with his conclusions. The moment new images of Atlas were released, one detail immediately stood out and sparked confusion across the astronomy community. The long familiar comet tail that observers expected to see appeared faint, narrow, or almost completely gone. For many watchers, this looked like another shocking change added to an already strange list. A comet without a visible tail feels wrong, especially after passing close to the Sun, when activity is usually at its peak. Initial reactions were mixed. Some amateur astronomers believed the object had lost material in a violent event, while others wondered if its structure had changed after perihelion. On social media, speculation grew fast, and theories quickly moved beyond science. When something disappears in space, imagination often fills the gap before data can catch up. This reaction was understandable, because the tail of a comet is one of its most recognizable features, and losing it feels like losing proof of its identity. The scientific explanation, however, turned out to be far less dramatic and far more revealing. Astronomers studying Atlas used specialized filters that detect diatomic carbon, a molecule that glows under sunlight. Observations from facilities such as the Lowell Observatory showed that the comet was still releasing gas and dust. The key difference was not what the comet was doing, but how we were seeing it. From Earth's position, the tail was aligned almost directly behind the nucleus along our line of sight. Instead of stretching across the sky, it collapsed visually into a thin shape that blended with the core. This effect is a powerful reminder of how perspective shapes observation. In three-dimensional space, objects do not change just because our viewpoint shifts, yet our interpretation often does. The tail did not vanish and it did not shut down. It simply rotated into a position that made it harder to detect with standard imaging. Once this was understood, the missing tail stopped being a mystery and became a lesson. What makes this moment important is not just the explanation itself, but what it reveals about scientific caution. Without careful analysis, it would have been easy to add another false anomaly to the growing list around Atlas. Instead, researchers showed how patience and better tools can separate illusion from reality. This also reinforced an important point. Despite its unusual origin and behavior, Atlas continues to follow the basic rules of comet physics when examined closely. Yet even as one question was resolved, attention quickly shifted to something new. If the tail was never gone, then what else might we be misreading when we look at this object from far away? And if visual tricks can confuse us so easily, what happens when the signals are not images at all, but something we hear instead of see? The discovery of a radio signal linked to Atlas instantly pushed the story into a new and far more sensitive space. Radio waves carry a special weight in human culture because they are tied to communication, intention, and the search for intelligence beyond Earth. When astronomers confirmed that emissions had been detected from this interstellar object, attention moved quickly from telescopes to deeper questions about meaning. Projects like Breakthrough Listen exist for one reason. They search the sky for narrow radio signals that might suggest technology rather than nature. History makes this reaction understandable. In 1977, the famous WOW signal briefly appeared in radio data and has never been fully explained. It lasted only seconds, yet it shaped decades of curiosity. With that memory still alive, any radio detection from a rare visitor like Atlas was guaranteed to trigger excitement and fear at the same time. The reality turned out to be less dramatic but far more informative. Using the Meerkat radio telescope in South Africa, researchers recorded signals at frequencies of 1,665 and 1,667 MHz. These numbers matter because they match known absorption lines produced by hydroxyl radicals. Hydroxyl forms when water molecules break apart under strong sunlight, which is a normal process for active comets. In simple terms, the radio signal was not a message being sent, but a chemical fingerprint being revealed. Timing played a key role in understanding this result. The detection happened shortly before Atlas reached its closest point to the Sun, when solar heating was at its strongest. During this phase, ice on the surface transitions directly from solid to gas. That process releases specific molecules that interact with radio waves in predictable ways. The signal confirmed that water ice was present and actively sublimating, which fits perfectly with known comet behavior. This explanation also drew a clear line between science fiction and observation. If Atlas were a metallic spacecraft or an artificial probe, these chemical signatures would not appear. Metals do not create hydroxyl radicals, and they do not mimic the radio patterns of evaporating ice. Instead of pointing toward intelligence, the signal strengthened the case that the object is governed by natural chemistry and physics. Yet the emotional impact of the discovery should not be ignored. Even when explained, the idea of hearing something from an interstellar object feels powerful. It reminds us how little distance matters when signals travel at the speed of light, and how quickly imagination can outpace evidence. Scientists understood this risk, which is why they were careful to publish details quickly and clearly, leaving little room for misinterpretation. Still, clarity does not always end curiosity. The radio signal closed one door, but it opened another. If every strange feature so far has a natural cause, why does Atlas continue to feel different from anything we have seen before? And if explanation alone is not enough to quiet suspicion, what keeps doubt alive even after the data speaks? Even after each strange detail found a natural explanation, doubt did not disappear around Atlas. This persistence matters because science usually calms suspicion once data aligns with known rules. In this case, the opposite happened. As answers arrived, new questions formed, not because the explanations were weak, but because the pattern behind them felt unusual. One reason is timing. The anomalies did not appear in isolation or across decades. They arrived close together, one after another, within a short observational window. A comet that returns intact after perihelion shows an uncommon chemical balance, accelerates in two directions, appears to lose its tail, and produces a radio signature that creates a sense of accumulation. Each event alone is explainable, yet together they create a story that feels heavier than the sum of its parts. Another factor is rarity. Interstellar objects are still new to science. Only a few have been studied in detail, which means researchers lack a broad sample to compare behavior. With limited reference points, every unusual trait carries more weight. When patterns appear in such a small group, it becomes hard to tell whether they are normal for interstellar bodies or signs of something exceptional. This uncertainty leaves room for doubt to survive even careful analysis. There is also a human element at play. Scientists are trained to be cautious, but the public reacts differently to mystery. The idea that something came from another star system already feels dramatic. When combined with unexpected motion and chemistry, imagination naturally steps in. This does not mean people reject science. It means the story touches deep curiosity about our place in the universe. In moments like this, explanation does not erase wonder. It often feeds it. From a research perspective, Atlas highlights the limits of existing models. Most comet theories were built using objects born around our sun. Applying those frameworks to a visitor shaped by a different star can produce gaps. When models stretch, confidence weakens, even if no rule is broken. Scientists know this, which is why many describe Atlas as a stress test for planetary science rather than a mystery solved too quickly. The object also raises a broader challenge for future observations. As detection technology improves, more interstellar visitors will likely be found. If each one shows unexpected traits, the line between rare and routine will shift. What feels suspicious today may become ordinary tomorrow. Until then, uncertainty remains part of the process. This is why doubt still follows Atlas, not because evidence points to something artificial, but because it forces science to operate at the edge of experience. And when knowledge meets its boundary, questions tend to linger, which brings us to the final reflection. If this object is natural, yet still so disruptive to our understanding, what does that say about the universe we thought we knew? Atlas now stands as a reminder that even familiar cosmic objects can still challenge human understanding. Its unusual chemistry, subtle acceleration, shifting appearance, and natural radio emissions all point to a comet shaped by a different star system, not a hidden machine. Yet the real impact lies deeper. This visitor shows how limited our experience with interstellar objects still is, and how easily new data can stretch old models. If a natural body can raise this many questions, imagine what future discoveries may bring. Share your thoughts below, subscribe for upcoming updates, and stay with us as we follow the next mystery crossing our skies.